where we start with chemistry, we like to start by just reviewing the important physics concepts that kind of underlie the whole thing. So 4 main pillars that we have here holding them up: electrostatics, conservation of mass and energy, potential and kinetic energy, and quantum mechanics. These are 4 things we're going to refer back to a lot throughout the course. So in each topic we do on every problem set, there'll be questions about potential energy or questions about electrostatic forces, because that's really what underpins all of chemistry. I like to start with this quote from this guy, Ernest Rutherford. He won the Nobel Prize in Chemistry in 1908, which would make you think, oh, he's a chemistry guy. But he once said, all science is either physics or stamp collecting. What do you think he meant by that? Yep. It's either physics or it's not science. So why wouldn't it be science? What do you think he meant by stamp collecting? What does a stamp collector do? More of a hobby. Yep. It's sort of meaningless. I'm not sure if he was calling it necessarily meaningless. But I think what he was saying is physics really is fundamental. You discover these laws, and everything, obeys these laws. The laws of gravity or law of relativity. Those ideas are fundamental. And then when you start looking at chemistry, especially back in his day, chemistry or biology, those were really about collecting facts and maybe ordering them in some way, but not necessarily having an underlying unifying explanation for it. So a chemist 100 years ago really knew lots of lists of, all right, this reacts with this reacts with this reacts with this is what they make. And then they'd kind of put them in some categories, like a stamp collector would do. They take their stamps, they put them in categories. A biologist, 100 years ago, a biologist was really about finding organisms and then categorizing them. Call it taxonomy. So taking them and putting them into categories and groups. Kingdom, phylum, blah, 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 genus, species. If you've taken biology before, you may have talked a little bit about that. That's really kind of old school ways of doing chemistry and biology. It's about collecting facts, bringing some order to them, classifying them, but not necessarily having an underlying explanation. So that's changed now. We've gotten to the point now where physics, these underlying physical laws, we can use to explain chemical phenomena. We can use underlying physical laws and applying them to atoms and molecules to then explain biology. So, 100 years ago, this was his view. I think nowadays what we can do is take those underlying physical laws and use them to understand more complicated things. In physics you study like a ball rolling down a hill, or an object falling through the air or falling in empty space. Those are really simple situations. Here we're studying billions and billions of atoms and molecules bumping into each other every second. But we can still use some fundamental ideas and apply those to understand. So what we do in this course is really build things from the ground up. We're going to start by looking at the model of an atom, applying some of these physical principles to atoms, and then expanding that out to how atoms bond with each other, and then expanding that out to how multiple atoms interact with each other. So that's what we're going to do in this class. And the first and probably most important idea that we use all year is the law of electrostatic forces. So it says F equals K times Q1 times Q2 over R squared. So we want to know, what are the different parts of this formula? What do they mean? What do you think F stands for? Force. So this is the force. All right. And then we have K. K usually stands for what? A constant. It's just a number. We don't really care what it is, because we're not actually going to do calculations in this class. If you go on and take a quantum mechanics class, take more advanced physics classes, you'll do the calculations that underlie this. We just want the concept. So the constant really is meaningless to us. We've got Q1 and Q2. Those, non-intuitive. These stand for the quantity of charge on object 1, quantity of charge on object 2. So these are the magnitude of charge on each object. And then R is going to be the distance between them. Really, in this class we're dealing with atoms a lot, which we essentially assume are spherical. So it's really the distance between their centers. Oh, that's interesting. All right, so that's what the formula looks like. In words, if we want to explain the important applications of this, well, the first one just has to do with the sign convention. So if these two things have opposite signs, if one of them is positive and one of them is negative, then what can we say about the direction of the force? Yeah, opposites attract. So you want to remember that opposites attract. And you want to remember that likes repel. Speaking of 80s music, which came up earlier, Paula Abdul knew that opposites attract way back in 1988 or whenever that was. But I'm assuming that's not one of the better 80s songs that anyone would still listen to. All right, what about distance? All right, farther away means weaker force. Closer together means stronger force. And then as far as the magnitude of the charge goes, greater magnitude of charge, plus 3 versus plus 1, what happens to the size of the force? Gets stronger. All right, so greater charge means stronger force. I'm not telling you anything you didn't already know here, but this is an important enough idea that I want to be explicit about it from the very beginning, because a lot of times students have trouble just referring back to these basics. When you're trying to explain something complicated, it's okay to come back to the basics and just ask yourself, oh, well, if I look at this situation, are the charges closer together or farther apart? Oh, they're closer together. So, yeah, it makes sense that the force would be stronger. Don't hesitate to come back to the basics. We will do it a lot throughout the whole year. All right, questions about Coulomb's law? Good. Other things we'll refer to a lot throughout the year. You've heard this before. We know that mass can't be created or destroyed. You can't make matter out of nothing, and you can't take matter and turn it into nothing. We call that conservation of mass. Same thing goes for energy. You can't create energy, you can't destroy energy. So if something gains energy, that energy had to come from somewhere. If something loses energy, that energy has to go somewhere. What is true of those things is they can be transferred from one place to another, or they can be transformed from one form to another. All right, so even though you can't create or destroy them, you can transfer them from place to place, or transform them from one type to another. And we concern ourselves a lot with those transformations. One side note, we don't talk about nuclear reactions in this class as much as I'd love to. It's not part of the AP curriculum. Turns out that mass and energy can be converted one into the other, but you really only see that in nuclear reaction. That interconversion exchange rate is E equals mc squared. So that famous equation from Einstein, basically saying that mass can be converted into energy. It's just when you convert a little bit of mass into energy, you have to multiply it by the speed of light squared to figure out how much energy. That's just a side note because we won't really discuss that. In chemistry, as far as we're concerned, we're not going to create or destroy mass or energy. Now, as far as energy goes, what we do a lot of is converting it from potential to kinetic or kinetic to potential. Let's see if you remember. First of all, what is our definition of energy? Because we talk a lot about energy in the class. We want to have an idea of exactly what we mean when we say energy. So what is energy? All right, we're wide awake. So energy is the ability to make stuff accelerate. Essentially, it's the ability to move stuff. In physics, you might have learned the definition. It's the ability to do work, but then you have to define, all right, what does it mean to do work? We will use, as our sort of simple definition of energy, the ability to make stuff move. So if you want something to move, you're going to need to use energy. It's an oversimplification to say it's the ability to make stuff move, but it'll work for our purposes. So throughout the course, whenever we say the word energy, I want you to think of some like imaginary currency that you can use to make things move. So it's like, I want, that rock to move from here to there. I'm going to pay this much energy to do it. That's what energy is. So then we have two types, kinetic and potential. What is kinetic energy? Most people remember this one. All right, it's energy of objects that are moving. So you can think of it like kinetic energy is energy that's already being used to make something move. So then what is potential energy? I'm glad you said that. So the response was energy objects have because they're not moving, or when they're not moving. Not necessarily true. Things can have potential energy even if they are moving. So I don't want you to think that's a common misconception, but I don't want you to think of potential energy that way. Potential energy objects have because of what? All right, so it's energy that's stored. that could be used to make something move. And how does it get stored? So potential energy is stored energy. But how do objects get stored energy? Can you think of something that has stored energy? A rubber band, when? When it's pulled back. All right, what else has potential energy? An apple you're holding in the air, any object you're holding in the air. Why does a rubber band have potential energy when it's pulled back? Why does an object have potential energy when it's held in the air? Yeah, because when it's released, there's a force that's acting on it that's going to make it want to move. All right? And it has that force on it because of where it is relative to something else. So the rubber band, because of the position it's in, if it's stretched, because of that position, that's why it has potential energy. The apple, when you hold it up, because it's above the ground, that's why it has potential energy. So it's stored energy that objects have because of their relative position. So gravitational potential energy is the simplest example for us to think of. We all have some experience with gravity. Things have gravitational potential energy around Earth because of where they are relative to the Earth. Okay? And we'll come back to that example in a little more detail. But you want to keep these definitions in mind. When we talk about kinetic energy, it's something's moving. Something is moving has the ability to make stuff move because it could bump into something else, and it's already moving itself. Something that's in a specific position might have the potential to move as well. So what are some examples of kinetic energy? Just throw some out there. All right, a ball flying through the air. All right, a roller coaster in motion. Can we think of other kinds? Maybe not big objects moving. What else is moving in this room besides, big objects? All right, electrons moving. So, electricity flowing through a wire, electrons moving through a wire. I think the example was actually moving around a nucleus, but also say, or through a wire. What are some other kinds of energy that involve motion? All right, so a rubber band when it moves back to its original shape. I'm thinking more. Let's think on a tiny, tiny level. What's moving, constantly? Yeah, molecules have thermal energy or heat, right? Because of that, they're constantly moving. So, thermal energy. So, how do you know what I'm saying right now? Sound, right? vibration of atoms and molecules in the air between me and you that then reach your ear. So sound is a form of kinetic energy. How do you see what I'm writing on the board? Light. Light is kind of a form of kinetic energy. Light is almost its own category, really. But you can think of light as a form of kinetic energy. I'll put it in parentheses because it really kind of defies, it really is kind of its own thing. We'll talk a lot about light next week. But we know all these different kinds of kinetic energy. Different ways that motion expresses itself. And in this course, really, heat and light are going to be the two most important for it. Because when we're dealing with chemistry, we're dealing with atoms and molecules, samples of atoms and molecules, and the most common ways that we're going to get information about them, well, we know when they get hotter, that means they're moving more rapidly, and we know that if they're giving off light, well, they're releasing energy that way. Those are the two most common forms of energy we'll deal with. So what we'll do on Fridays, we'll pick this up and kind of finish laying down our fundamentals for the year. You can start working on that first problem set, which again, trying to get done for Monday. And we'll call it a day there.